15 years ago, and then he moved to Chicago as a Hubble scientist. And after that, he went to UC Davis, and he has been there since then. Lloyd has done a lot of interesting work on CMB and CID, and I think you're familiar with his work. And he is a part of Planck and SPT, and he's going to talk about this great stuff that we have learned from these experiments about CMB and CID and cosmology in general. So please.
Thanks, Amir. It's always great to come back to CITA. It's now 15 years since I left. I've been largely motivated in the work I've done by interest in fundamental physics and using cosmology to learn about fundamental laws of nature. And indeed that's happened in the past 15 years. There's been things we've learned from cosmology. But also now for almost 15 years we've had this standard model of cosmology, lambda CDM, and it has been, for someone interested in finding new physics, it felt quite unfair at times how well this model has performed. And instead of just griping on how fair it is, I've decided to really marvel at how amazing it is that this model works, and works at, in particular what's marvelous is the amount of details we have to get right in order for that success to be realized. So that's what I'm going to be talking about today. What do I mean about the success? Well, here's perhaps the most dramatic example of it. This is the microwave background power spectrum and measurements from WMAP. This is the WMAP 9-year final measurements of the power spectrum. And you can use these measurements and constrain the parameters of this model. There's 6 of them using these data, plus polarization data from WMAP, and make a prediction for the rest of the power spectrum. And this is not a best fit model shown here. This is the 68% confidence prediction of the CMB power spectrum, assuming lambda CDM, the standard model of cosmology, and given the WMAP data. So this tiny band here has some width. That's the 68% confidence region. This is where the power spectrum should be. And moving on from WMAP and including data from ACT, which I imagine everyone here at CITA knows about, is Atacama Cosmology Telescope, and also the South Pole Telescope. The measurements basically just fall right on this prediction. It's quite an astounding success. And if we go on further to Planck, the same thing again, and now these error bars are so small that to really appreciate that Planck did anything new here on the power spectrum, we need to zoom in on some regions. And so here's a zoom in on the 4th and 5th peaks, and you can see this gray band of the prediction given WMAP, and the red line is the new best fit given the Planck data, and you can see these extraordinarily tiny error bars here, and lambda CDM is still providing a good fit to the data. Now, showing you this, I feel terribly dishonest if I didn't also show you there are some problems that cannot possibly be a problem with the lambda CDM model. But there is an offset at low L, so this is the first peak here, a small offset, 1.3% in the amplitude of the maps. There's a mismatch in what appears to be a calibration issue. This is not yet, this is still not yet understood. So this problem exists in the data. Obviously, we're observing the same amount of sky. This has nothing to do with lambda CDM, and this will get resolved. So here are the measurements from Planck, seen again now in a different plot, together with residuals from this best fit standard model. And it appears that this lambda CDM model provides a very good fit. So what I want to do is dig into some of the details that we have to get right that are involved in calculating these model spectra and other observables given the lambda CDM model, so we can further marvel at how this all ends up coming out consistent with the data. So first I'm going to talk about something called the integrated Sachs-Wolf effect, then talk about gravitational lensing, photon diffusion as the universe transitions from being ionized to being neutral, and then briefly some words about the future. So here, let me just first run through just a brief history of the universe according to the standard model of cosmology. So here we are. This is the scale factor down here. So this is time-like variable parametrizing the expansion of the universe. Scale factor here of 1. When the universe was 1,000 times smaller than it is today, it had a scale factor of 10 to the minus 3. This is, we've gone through these epochs right now. Just very recently, the universe has become dominated by a cosmological constant. Prior to that, the dominant contribution to the energy density was cold dark matter. And then prior to that, radiation, background of neutrinos and photons. This is the transition when the universe transitioned from being ionized and opaque to being neutral and transparent as the nuclei combined with electrons as the universe cooled, and then the photons could travel freely since this epoch. Going back further, we have some mechanism for generating the primordial fluctuations, presumably inflation. And inflation, we don't know how far that goes back, but far enough that it's way back here that the fluctuations are generated that we observe today in the microwave background. Now I'm going to step you through different parameters that, the 6 different parameters that there are in the standard model. So we have 2 that have to do with the amplitude and scale dependence of these fluctuations. So the amplitude AS and this NS governs how those fluctuations depend on scale. Obviously the photons are an important part of the model, as the neutrinos. We don't actually have any free parameters associated with these. In the model, the microwave background photons are a black body, and we've measured that temperature very well. So this is basically effectively fixed. And then making standard assumptions about neutrinos and when they decouple from their thermal production and when they decouple from the plasma. This is also, the density in neutrinos is not a parameter in the standard model, although they play an important role. Back this far, weak reactions are in equilibrium, so this is when the neutrinos are produced. They fall out of equilibrium here, soon before the electrons and positrons annihilate with each other, dumping their entropy into the plasma. We parameterize the baryon density, rho b, the density of cold dark matter, the energy density associated with the cosmological constant, and then finally, as the photons travel on their way to us from the last scattering surface, the universe reionizes again. In principle, we could calculate when this happens. In practice, we need to parameterize it, and so we have another parameter here. When does the universe reionize? the universe reionizes, and that has an impact on the microwave background because about 10% of the photons traveling on their way to us scatter off of the reionized intergalactic medium. Okay. This has never happened to me before. I'm going to turn off Google. Okay. So here are the six parameters: amplitude and tilt to the primordial power spectrum, the matter content, and the scale factor at reionization. We usually write the densities in particular units, and that we label with these symbols. And this gives us, these things are quantities then of order unity. So that's just a quick review of what this standard model is. And now let me say something about the integrated Sachs-Wolf effect. First, explain what it is. So in a universe that's matter dominated, and in the standard model, we went through a substantial period of matter domination. The density fluctuations, departure from complete uniformity, drop like a to the minus 2, the scale factor to the minus 2 power. If it weren't for any clustering happening, this density would drop like a to the minus 3, as the mean density of everything is dropping like a to the minus 3 due to dilution. But the clustering that's happening is keeping this, is making it so this is only dropping like a to the minus 2. So that leads to, if this alone were happening, the gravitational potential would decrease with time. But at the same time, the expansion is moving peaks and troughs in density further apart from each other. That increases the gravitational potential. And the net result works out that actually this potential stays constant. So in a matter-dominated universe, gravitational potentials, at least to first order in perturbation theory, don't evolve. If you have something, in addition to matter in the universe, that's contributing to the expansion but isn't promoting the clustering of matter, then the gravitational potential will decay. And here's a little cartoon of that. Here's a photon entering a well, a potential well, at a certain depth. And the photon gains energy as it falls into that well. And then, since the depth of this well decays, the photon does not lose as much energy as it, does not lose as much energy as it gained when it's working its way out. So the potential has decayed while it was in there. So if you compare a photon that traveled through a potential well, and you look in a different direction towards one that traveled through a potential hill, that effect will be opposite. So this effect introduces new anisotropies. And this happens at late times exactly because of that cosmological constant contributing to the expansion, which leads to these gravitational potentials decaying. So we can actually find this effect. Here's a stacking of CMB maps from Planck towards different directions. Here towards superclusters, here towards large voids, and you can see it getting a little bit hotter here and a little bit colder in the directions of voids. And this panel just shows a difference between these two. So we can directly see what we expect from the integrated Sachs-Wolf effect at late times.
And sorry, so what is the rest of the structure? Is that noise or around?
Yeah, so that's just noise from the fluctuations that have nothing to do with the right. So that late effect substantially increases the power here at late times. There's also another era where this integrated Sachs-Wolf effect is important, and that's because as the photons start to propagate freely here, we're not that far into matter domination, and there's still some radiation around that's contributing to the expansion rate. And that has a huge effect. We don't have any direct tracer to use like we did with the superclusters and voids for the late ISW effect. But, at least according to our models, early ISW increases the power here in the first peak by about 30%. We can, in a model-dependent manner, actually detect this early ISW effect. So here in this paper, we introduced a scaling of the ISW term, just an artificial scaling of the ISW term by this parameter AEISW for early ISW, and varied it along with the other physical parameters. And this is it basically detects its presence at about 20 sigma. So this is just showing that this is a dramatically large effect, and the standard model, since we're scaling the standard model value with this parameter, the fact that we get a result, no matter which of these model spaces we're looking in, we get a result that's consistent with 1, is a success of this standard model. That's N effective. So, sorry, I didn't have a better plot to use on this. Well, N effective, which we'll get to later, is a parameterization of how much energy density there is in the neutrino background. So for NF equals 3 is the standard model value. So here is a standard model on this plot.
Sorry, ignorant question. Photon energy density decreases more rapidly than matter energy density. Lambda decreases more slowly. But do they really have the same effect on the sign of the gravitational potential? I mean, the sign of the effect of the gravitational potential is the same.
What they're contributing to is the expansion rate, and they're both relatively smooth, right? One from the pressure, right? Okay.
So I assume that you can't get the second derivative
Of the potential.
Yeah, because essentially what you're doing is getting phi dot as you're going through recombination, or maybe a delta phi integral. But you know, there's more information across the fuzziness.
So.
I mean, it won't be much because you know it's just changing from the the relativistic non-relativistic transition. It's a very, very continuous change.
Right.
You know, I don't know what the sensitivity would be in that.
Yeah, I don't know. We haven't tried.
Check
but,
alternate theories of gravity, Lloyd. Same method.
So this integrated Sachs-Wolf effect, one reason that I bring it up is that, at least before we had Planck, with South Pole Telescope data combined with WMAP, this was actually the dominant source of our constraints on neutrino masses. So let me tell you about that. Adding in neutrino masses, the major effect they have on cosmology is to change the expansion rate. So this is redshift down here, and here's the ratio of the Hubble parameter as a function of redshift as we vary the neutrino mass. And keep things constant that tend to be well determined from the microwave background, such as the dark matter density and the angular size of the sound horizon. At low redshifts, increasing the neutrino mass increases the expansion rate because now you have the energy density in the neutrinos redshifting more slowly because of the presence of their mass. Right? The momentum's going down like 1 over A, but now their energy is no longer going like the momentum. It's going like, switching to being like going like p squared over 2m. So, plus the rest mass. So that increases the expansion rate as this component, this neutrino background, now redshifts away more slowly. And then at z equals 1, we actually transition because in order to actually keep the C and B observables fixed, such as the angular size of the sound horizon, we need to, since the expansion rate got decreased here, increased here, we need to decrease it here. We do that by decreasing the value of the cosmological constant. So we get this, increasing the neutrino mass, we get this particular change to the expansion rate.
So this value is equals 1, it's just you're picking that out of here. Why is it switching over?
Why is it switching here?
Yeah.
This is because that's when we basically switch from being matter dominated to being cosmological constant dominated. So it wasn't this isn't chosen in this place. It just that's where it turns up. And then this is an effect on the microwave background. This is the ratio of C and B power spectrum with varying neutrino mass to C and B power spectrum with zero neutrino mass. And that here we get a slight boost to the power as we have an increase. We have an increase to the increased expansion rate is causing the potentials to decay, and as the photons traverse these potentials, new anisotropies are created. Out here, the neutrinos are actually contributing to growth. On a large enough scale, the neutrinos actually can cluster, and basically out here we're decreasing this early time ISW because effectively we're getting a conversion of what would have been radiation to what's acting like matter instead. So the fact that the neutrinos can cluster actually supports the growth of the gravitational potential, supports keeping the gravitationals constant more than they would be otherwise on scales large enough that the neutrinos can actually cluster. And then there's a larger effect out here because, as I told you, that expansion rate out here has to decrease because we have to decrease the cosmological constant in order to keep that distance to less scattering fixed. And this is the dominant effect, the important effect, what was providing constraints on neutrino mass from the C and B alone. Here's neutrino mass down here, and the posterior probability of it given the data from SPT and WMAP7, and we see a peak out here at 1 eV, although 0 is perfectly fine. Not real, definitely this is not any kind of detection. And the dominant physical reason for this curve having features out here is that early ISW effect. So it's pretty amazing that we are learning something about neutrinos. Neutrinos are difficult to study because of how weakly they interact, so instead we're learning about them using gravity.
Sorry, in the previous plot, you had different L's corresponding to different times. So is that roughly the angular scale corresponding to where the power spectrum peaks?
So the later effects show up on the later times show up on larger angular scales because you're sensitive to larger and larger volumes. So basically, the late time stuff isn't important out here because on these scales you're traversing so many different peak, hills and valleys that it all washes out. The effect washes out. So the late time effects don't show up out here because of that washing out, and so you're only sensitive to the earlier time effects out here. So another effect that's terribly important for predictions of the standard model, as well as understanding constraints on departures from it, is gravitational lensing. So you'll hear a lot more about gravitational lensing from Duncan Hansen on Friday next week, as I understand it, in the physics colloquium. Astronomy colloquium, okay. Was it this week?
I think it's this Friday.
Okay. So Duncan actually made this map for me. So this is a map of the full sky map of the microwave background from a simulation, and a simulation with a unphysically large gravitational lens in it. Well, maybe physical, but it's certainly not one that occurs in our universe. And so, can you see where it is? Mike's insulted by me even asking. And so you can see it because that lens does distort the statistical properties of this noisy background. And so you can see that the size of a typical hotspot is larger here, which has been magnified by the lens, than they are off around here. And in that manner, we can detect the presence of lensing in microwave background maps. I mean, using more sophisticated techniques than just looking at it.
That would say see the shear too. Do you use the shear as well?
Yes.
Yeah. Okay.
Yeah. So basically, I mean, you can think of this as making local measurements of the correlation function, and in different directions, and seeing whether it's sheared or magnified. Yeah, those both come in. So if you weren't seeing it, we can flip back and forth, right? And you can see the lensing pop out. So by looking for these signals over the sky, we can make maps of the deflections that the photons have suffered as a result of gravitational lensing. Here's a map of deflection amplitude from Planck. So the color here is just encoding the amplitude of the deflections. This is as Duncan will describe to you, this is a Wiener filtered map. So showing modes just from L equals 100 to L equals 10 to L equals 500. And there's a lot of noise in here too. There's almost as much noise in here as there is signal. But altogether, statistically, this is a 25 sigma detection of lensing. And one way of verifying it is to compare it with another tracer, deep tracer of mass in the universe. So here's a 545 gigahertz map from Planck, and you see all this emission from dust in the plane of our galaxy. Well, there are other galaxies in the universe, and they all have dust in them. And so if we look away from the plane and blow up a piece here, there's also fluctuations out here. And the dominant source of these fluctuations is from the dusty emission from galaxies on our past lifetime. So we can compare, we can take a deflection map, and everywhere there's a hot spot in the infrared background on that 545 gigahertz map, we can stack the deflection map there. And go find another hot spot, stack on top of that the deflection map for that part of the sky, and repeat. And what we see is, here, stacking on hot spots, the deflection pattern that you average down has the expected form. So we're seeing that the tendency, so where we have these hot spots, that's because there's more mass in that direction, right? More galaxies in that direction, emitting this infrared light. And that mass is lensing the light from the microwave background. So we pick that up, averaging down the deflection maps, we average down to this pattern where we see the deflections responding to the mass. You have the opposite behavior on cold spots, as expected, and then as a check, stacking on random spots, we get no signal at all. This is also seen in SPT cross-Herschel data, and this strong correlation is something that we predicted with a graduate student of mine in 2003. So success of the standard model is that this E mode polarization is lensed to B modes as predicted. So the polarization pattern on the sky can be decomposed into curl-free modes and gradient-free modes called E and B modes. But I don't really need to explain those to you, as I found out while I was flying here. My son, traveled out here with my son, who's 15, and he said, "Oh, Dad, look, check out this quiz bowl program I have on my computer." First or second question that popped up was this one. So this is in the standard analysis of C and B polarization, the polarization field is decomposed into the spin-weighted variety of these mathematical objects. I couldn't believe it. I was actually so stunned I got the question wrong.
Who is this for?
This is some. So there's some quiz bowl thing that he's participated in, and there's also a there's a set of questions that have been collected are now on the internet, and you can just take this stuff on on your computer. It is the way it proceeds though is they give the most obscure thing first, and then they slowly give more information, and you get if it takes you longer to get it, then you get fewer points.
Oh, I see. There's a lot of obscuration for a relatively simple answer. At the end.
That's right. The answer is spherical harmonics,
Yeah,
right?
yeah.
And so this is an right. So
I thought it would be a bit of a challenge. But,
yes. So here's the simulation of the unlensed temperature field and the E mode polarization intensity in the CMB and the B mode. If we don't have any primordial sources of B mode, so this is just should be just 0 here. And the effect of lensing moves stuff around in Fourier space, and it also affects this E and B decomposition. And if you lens this, you get some leakage from E into B. Down at a level about 10 times smaller than the E mode amplitude. Here's a map showing a lot of emission from those dusty galaxies I mentioned before. This time not from Planck, but from the Herschel satellite. This is time we got to image the SPT deep field for entirely different reasons. And we use this though as a tracer of mass in the universe, from which we could figure out how the lensing should be happening. So here is the E mode map from the South Pole Telescope. Here on that same part of sky is a lensing potential determined from that CIB map from Herschel Spire. And this is the predicted amount of B mode amplitude there should be because of how this lensing potential will distort this E and make some of it into B. So what Duncan did is he took this synthesized template and cross-correlated it with the B mode estimate in our in that map. And here is the B mode power spectrum, the prediction of the standard model due to lensing, and here's the 150 gigahertz crossed with this lensing potential to create a B mode estimate, B mode template crossed with the SPT data, B mode, and other versions see results that are, again, consistent with the standard model. So going down to weaker and weaker signals.
So the CIB 5,
Yeah.
So there was an estimator of this, and it must have a certain amount of uncleanliness attached to it.
Right.
So there are some assumptions that have gone in to get the gravitational potential out of the Herschel observations. What are those assumptions? Are they,
So-
is it just large-scale linear bias?
I believe so. I think that, if you then ask the question, well, I mean, we've measured this correlation, right? And you can ask with the amount of uncertainty in the level of that correlation, how much would that kick the amplitude of this around? I think it's negligible compared to the other errors.
Oh, yeah. And going back to the phi CIB map that you had prior. So in a sense, that's kind of a Wiener filtered picture coming from Herschel's spire with the linear assumption. And so the issue is, what do the fluctuations look like?
So, yeah, and I wish I could show you.
Well, actually, Duncan tends not to show the fluctuations either, although we're going to do it in the next Planck paper, definitely. But, he tends not to show that, whereas I think that's sort of a key thing to get an idea of where the uncertainties are. I guess it's probably fairly uniform, except that probably there's a high degree of correlation of the errors in that. That is to say, there's a complicated interaction of the noise covariance, I mean the effective noise associated with phi that would correlate different regions on that phi map.
There have to be.
Yeah,
because
of course,
we're
yeah.
dealing. Because we're dealing with something, a tracer of mass, and then we're taking we're effectively taking intervals over that to get the phi. Right? So in the Fourier domain, though, those correlations won't be as large. Right.
True, but you're drawing information which is from an inhomogeneous data set, and maybe it's sufficiently homogeneous that it is approximately k independent, but it's unclear. You'd have to look at that in some detail. Especially, you'd have to understand a lot about Herschel's spire. Although it may well be true. In fact, I guess why not?
So here in the E-mode map, next to every hotspot there is a cold spot with the same shape. Is that a ringing because of the filter?
Because of what modes have been filtered out, yes.
And that's also why it has this shape.
Yeah. The filtering's been anisotropic.
It's anisotropic filtering?
Yeah. We can also get constraints on the matter density from lensing information in CMB maps. And let me just quickly say something about that. One thing we did before Planck, when we were analyzing our CMB power spectrum measurements from SPT, was we measured the parameters from just SPT. So if we didn't include the WF7 data, what do we get for the standard model parameters? And this is another success of the standard model. They're all consistent. So this is the parameter from SPT divided by the parameter from WMAP minus 1. They're all consistent with each other to within in the error bars. And but it brought up a question for us. Well, how is the matter density being constrained by the SPT data? This early integrated Sachs-Wolf effect is very sensitive to the amount of matter there is, exactly because that sets when matter radiation equality is, so it determines how much radiation is around after decoupling, plus an effect I won't talk about. SPT is measuring at smaller angular scales, where that early ISW effect is not showing up. We don't have any sensitivity to it. All those modes have entered during the radiation-dominated era, and signatures, the usual signatures of matter density don't come through. Yet we control it anyway, and the major source of information on it turns out to be from gravitational lensing. So this parameter from SPT, the power spectrum at high L is sensitive to how much lensing has occurred. That depends on the matter density, and so this parameter is determined through a completely different mechanism, and yet is consistent with what you get from larger scales. Finally, for gravitational lensing, this lensing is now the dominant.
Can I ask a question
Yeah.
about that? So SPT has to normalize, has to define its amplitude, and so it's tried to do it with WMAP, or did it do it with some other?
No,
with Planck, you can do it with Planck,
Right,
of course,
right.
and now it's been done with Planck,
Right.
and that causes an adjustment. And the question is, how exactly was it done? Was it done with WMAP 7 with
Yes.
power spectrum overlap?
Yeah. Yeah.
And how good was the power spectrum overlap?
The power spectrum overlap left. There was, I think that in a model independent manner, where you just want the power spectrum to agree, was 2.6% in the maps, the map calibration. So like 5% in power. And then the model, when you include the model, then that shrinks. You know, your calibration shrinks significantly.
Yeah, right. Okay, so now, in the old days, before you were doing a WMAP, you were using something else, probably, what, I don't know, sources or something.
For SPT,
Yeah. How did you do the calibration before?
it was always with WMAP.
Oh, it was?
Yeah.
But in the very first SPTs, your L's were too high.
We were using a different filtering of the data that extended to larger scales and doing a cross correlation on the map.
I see. So
Yeah.
even though you weren't concentrating on that region, you were using it
Yeah.
to try and do. And did that change at all as you improved your power spectrum?
I don't think it's changed significantly. I mean, certainly.
And so does the shift of the amplitude of SPT that's driven by Planck is not that large.
It's small. I mean,
But does that help to alleviate some of the parameter issues?
no.
Doesn't. So that's irrelevant.
It
So
is.
that amplitude fix is
Yep.
irrelevant.
Yeah.
Does George agree with you?
We can talk. Maybe we can talk more about
Yeah,
that.
Maybe classified.
At dinner. Some of it's classified. There's more I could say that isn't.
Yeah,
But
Yeah, okay. Yeah,
it's an interesting story,
good. Mhm.
ongoing.
Yeah.
So you're filtering the low L modes in SPT,
Right.
And that's where WMAP has good data.
Right.
How much overlap do you have after filtering?
So we go down to 650 with SPT. L equals 650.
Okay.
So I mean, basically 650 to 800. Finally, gravitational lensing is now responsible, at least from the microwave background alone, our best constraints on some of the neutrino masses. So neutrino masses are both affecting the expansion rate, as I showed you, over time, and they're affecting the growth of structure. Both of those affect how the CMB gets lensed. if we take the Planck temperature power spectrum and measure the posterior probability of neutrinos, there's no desire for any neutrino mass, and we get a fairly tight constraint. If we artificially let the amplitude of lensing vary by introducing scaling like I did for AEISW, some scaling of the lensing by AL, and allow that to float, then we remove the lensing information and the constraint relaxes like this. So the dominant source of information that we have about neutrinos is actually coming from how they affect how the C and B gets lensed, which is pretty extraordinary. Speaking of Planck, though, and parameter constraints, I think I just have time to get this important result out. So one of the, when we released the Planck data at the end of March, we were unsure what story to lead with, but we certainly didn't care about the shift to the age of the universe, but the Onion did. So that got us into the Onion. Universe older, I'm not sure what the wider is about. Universe older, wider than previously thought. What do you think? How embarrassing. Typical. You give birth to a few trillion galaxies, and then people just talk about how old and fat you've gotten. And then I couldn't believe it. Norm Murray, they actually asked Norm Murray. He said, what do you know?
Very, very well done.
I'm glad you showed up, man. And let's see. I think I do have time to say, to actually go on to the scheduled talk. And that's the importance of photon diffusion and what we're learning from that. So there's two important scales. Well, there's a third as well. Two important scales for what I'm talking about now in the microwave background. One is the angular size of the sound horizon that I've been mentioning, and that controls the location of these acoustic peaks. And as such, is something that we've measured with tremendously high precision. It's the ratio of the size of the sound horizon on the last scattering surface divided by the distance to the last scattering. Right? It's that horizon in projection. And then there's this diffusion scale, which we weren't really resolving well with WMAP, but we are now with Planck. And as the photons are in the plasma and the electron density starts to drop, they start to diffuse. The amount they diffuse before last scattering, that typical distance, is this diffusion length, RD. And that diffusion, since it's going in random directions, if you have a hot spot here and a cold spot here, and they're separated by less than a diffusion length, that anisotropy gets suppressed. Because some of the hot stuff's traveled over here before scattering, some of the cold stuff traveled over here before scattering. And so we have this suppression of power out here at small scales. We can actually use that to determine the expansion rate near recombination. So the sound horizon is dependent on the amount of time we have to expand until recombination happens. So it goes like that inverse of that expansion rate. Whereas the diffusion is a random walk. And so it goes like the square root of time. It goes like h, so it goes like h to the minus 1/2. This ratio is observable, right? We can observe the effects of theta d and of theta s. And that goes like h to the 1/2. So so we can observe this, and it depends on the expansion, the square root of the expansion rate. So we can use that ratio of scales to learn about the expansion rate. One thing that having extra neutrinos do, increasing the energy density in neutrinos, is to change the ratio of those scales. And here's a simulated map where you can see that effect. Here's the diffusion scale in this model and the sound horizon. So you can see that there's not much structure below the diffusion scale. That's all been wiped out by diffusion. And if we go from NF equals 1 to NF equals 10, that ratio changes. Here we're doing it we're changing the parameters in a way that keeps theta s that is so well determined fixed. And you can see the impact on the maps. Going from NF equals 1 to NF equals 10 increases the expansion rate dramatically and thereby increases the amount of diffusion relative to the sound horizon. So from that we can determine we're sensitive to the effective number of neutrino species. And the black curve is from the CMB data alone here, and we get a value that's completely consistent with 3. Helium also affects that ratio. Helium affects the damping scale as well, because basically helium is, because of the neutrons in helium and because helium is a neutral atom through recombination, helium gobbles up some of those free electrons. There's fewer around, and so that affects the diffusion process. And here are results from W7+SPT on NF and YP. Here's the standard model value, consistent with the predictions for YP from Big Bang nucleosynthesis. And we see the data are consistent with it. And then also, with Planck, we have a similar situation, somewhat tighter constraints. And with that tightening, the point has also moved into even more into the central region of this confidence contour. The color here is this theta d over theta s. So the tight part of this ellipse is what's constrained by this measurement of theta d over theta s. Other effects that I haven't mentioned cut this off, going in other directions. One thing I want to mention is that we would be, if it weren't for this dumping of the energy of electrons and positrons into the plasma after the neutrinos decouple, then if that had actually happened surprisingly before neutrinos decoupled, then we'd have NF of about 12 is what we measured. So we're actually strongly detecting the effect of what I'm calling this neutrino cooling. Neutrino cooling because it's heated up the plasma relative to the neutrinos. So, so I've tried to convey to you, what's that it really is marvelous what's going on. The effects that we're seeing validated in this precision data is pretty extraordinary. But if you really just want to, see evidence of new physics, we do have some reasons to be optimistic. One, we don't, we're talking about the lambda CDM model. We don't understand the cosmological constant, or even if the dark energy is a cosmological constant. We don't know what the cold dark matter is. These are key ingredients of the model. We don't know the physics behind inflation or whatever the primordial fluctuation generator was. We don't know the origin of the excess of matter over antimatter, clearly an important thing. So maybe we'll be in for some. There's no strong theoretical reason to expect this model to be the last word. Another reason to be optimistic is that we're going to make great progress in measurements that are easy to interpret. So from CMB polarization and the lensing we can get from that, here's a forecast of how the lensing power spectrum, now constrained something like this blue curve, will be constrained from SPT3G that you'll hear more about from Duncan on Friday. In addition, we'll have more measurements that are easy to interpret from high precision measurements of baryon acoustic oscillations and the history of the expansion rate you can reconstruct from that, and distance versus redshift you can reconstruct from that. And these types of data sets combined are going to take us from a current situation, for example, giving constraints on NF and M nu like this, to this situation where these axes are very different here. And just so you don't have to deal with mapping those axes onto each other, here's, if this is shrunk down appropriately, it's in here. So there's a lot more precision to come. So let me just summarize here. I told you about some of the successes of the standard cosmological model. I've told you about why I think this is really quite marvelous. And again, these successes require the cosmic neutrino background that's been predicted. Measured, this has to be there at greater than 10 sigma. And it has to be appropriately cooled as expected. An amount of helium has to be there that's consistent with predictions from Big Bang nucleosynthesis. We have the expected amount of the early ISW effect detected at 20 sigma in old data. And in a number of ways, we see the expected effects of gravitational lensing, including most recently this very small amount of B-mode power pulled out of the SPT maps. So, thanks for your attention.
What does 3G stand for? Third generation?
Yeah, I hate the name, but we seem to be
Not
stuck
the
with
number
it.
of, it's got nothing
I mean,
to do with
3G is
the amount of
yesterday's
stuff.
technology,
Yeah.
but yeah, it's third generation. And now, you know, so in the snow mass process, right, this is, so then this was not SPT 3G, but a generation beyond that, stage 4 CMB.
And what is the time scale
For this?
you know?
Well, I'm not sure about this. For SPT 3G, observing in 3 or 4 years.
When is DESI supposed to be?
DESI is supposed to have first light in 2018. Or maybe 2017. And they're I don't know if you've all, so they're about to go into their CD1 review, if any of you know DOE speak.
So a couple slides back, when you were showing the posterior distribution for the NF, what do you think about when you combine things with H0 and with the BAO, and things move into different directions?
Yeah,
Just
yeah.
going forward.
In fact, I have another slide that can highlight that even better. Let me escape from this. This one. No, no, this one. So this is, with BAO, this is done as not the usual way it's done, but written as the angular size of that sound horizon when the scale factor is 0.64, or that's a z of 0.57. Okay, so this is, you can use that feature in the galaxy correlation function from the sound horizon to measure that angular scale. And here's the Riesedahl measurement of H0. So this is what one thing Amir's talking about here is that we don't have wonderful agreement with the Riesedahl measurement of H0. And Amir's also referring to one possible solution to this, which is to, instead of just having lambda CDM, actually let this NF vary. And if you increase NF some, then you can lighten that tension between BAO, CMB, and the Reset-L H naught. Now, I think it's way premature to jump to this. It's a 2.5 sigma discrepancy with H naught, and well, we're learning more, with our continuing analyses of blank, and our understanding of H naught will be evolving and tightening up, and we'll learn more. Right now, it's I think that NF equals 3 is actually looking really good.